I think exercise 1 and 3, we covered them. And then exercise 2, I also have so exercise 3 is actually a homework question in the undergraduate courses. So I spent the whole video talking about homework 2. Yeah. So I think if you need some details, you can revisit that video for exercise 2. So maybe we can talk about exercise 4 and 5 for now. Is that okay for everyone? Yeah, so that's the part that we skipped last time, right? Or we did not touch upon. Yeah. Okay, so let's see. Yeah, so this would be homework 8, exercise 4. Okay, so I think we have x1 from a mean of 1 and sigma. And then x2 is coming from a normal with mean -1 and sigma. And also x3 is coming from a normal of 0 and then sigma. Yeah, so it seems like they share the same variance, but different mean values. So we are trying to show that, or to talk about what is the distribution for q of x over sigma squared. And q of x is having that particular form. Okay, so maybe we can first write down x is in terms of x1, x2, and x3 as a column vector for a 3-dimensional normal with this particular mean vector and then a sigma square identity of 3. So that would be the multivariate normal. Okay, so first let's take a look at the q of x. Which is x1 squared plus x2 squared and x3 squared. And we also have 2 copies of x1 and x2. Yeah. So actually this quadratic form, or this summation of a few terms that involving square, we can express in the form of x transpose multiplied by b multiplied by x. Okay, with the x defined in this way. So now the problem is that how can we define our matrix B? So yeah, so here you can find the B in the following. Well, it's basically just reading off the coefficients for that. So let me write down what I meant. So this is, I think Q has a, okay, Q has a 1 over 2. Okay, no wonder. Okay, so this is Q from the question. And now we're going to write it as a matrix vector multiplication. So we can write it in the following way. So a row vector, so a 1 by 3, and then multiply by 3 by 3. And that is going to be a 1, 1, and then a 2. So yeah, so if you multiply the column vector and the row vector by this matrix, you are basically just collecting the product term with the coefficients assigned here. So you have 1 copy of x1 squared, 1 copy of x2 squared, and then 2 copy of x3 squared, and then also a interactions for x1 and x2. So the entries for 1, 2, and 2, 1 are also 1. And then when you sum them together, you have 2 copies of interactions. Okay. Yeah. So we are able to rewrite the function of Q in terms of matrix and product, matrix vector multiplication. Yeah, so let's define this as B, and then this is another 3 by 1, so this is 3 by 3. Okay, so what we want to comment on is that the Q of x over sigma squared. So we essentially have a matrix of x multiplied by b multiplied by x over sigma squared. So here we're going to apply one of the theorem. So first of all, let's revisit some property of this matrix B. So here we can see that B is symmetric. From just, you can declare that as just by looking at it. And another thing is that this is idempotent, which means that B multiplied by B is also equal to B. Yeah. So yeah, what are some theorems that we can use here regarding matrix of idempotent and symmetric, and also we are talking about the quadratic form. So is there any theorems from your lecture notes we can use here to claim or to comment on the distribution? Okay, so yeah, so in one of your handout, I think it's called quadratic form of something of quadratic form of random normally distributed random variable. In that handout, maybe let me write it down. So in that handout, there's a theorem. That theorem's claim that when B is symmetric and idempotent, and then you have this formulation of this quadratic form, then this is going to follow a chi-square distribution with degree of freedom trace of the matrix B. So, and also when X is following a normal of, let's see, of, maybe I just not comment too much. Just take a look at the theorems that you guys derive or prove in the lecture notes. Yeah. And then we can use that theorem to claim that this Q of X over sigma square is following a chi-square, and then trace of B. So we define the B, the matrix B is actually the 1/2 multiplied by this part. So the trace of 1/2 and then 1, 1, 0, 1, 1, 0, and then 0, 0, 2. Then this is equal to 1/2 multiplied by the trace of this matrix. So the trace is just the sum of the diagonal elements. So it's just the 1/2 multiplied by 1 plus 1 plus 2. So it's equal to 2. So this is just a chi-square degree of freedom 2. Yeah. Any question or comments? Yeah, so maybe let me just summarize. So the question is that we are given these three random variables, and then we are given a formulation of this Q. And we are interested in the distribution of Qx over sigma squared. So what we did here is that, first of all, we define, or we re-express the function of Q as a scalar to a matrix vector multiplication. And then we find out that the matrix B, the one that we define, or that we read off the coefficient from here, is actually symmetric and idempotent. And then we apply the theorems from your handout that you guys show in the derive in the lecture, that whenever you have these conditions satisfies, and then this over sigma square follow a chi-square distribution, trace degree of freedom trace of B. And then we just calculate the trace from here, and then this should be your conclusion for the question. Is there a question or comments?
So if B is
Yeah.
idempotent, we just need to calculate the trace of B, and that's.
Yes.
Is it like there's a proof with?
Oh, I think it's from the lecture, from the handout. Okay, then let me. So this is the name of the handout. Distribution of quadratic form of normally distributed random variables. Yeah. And then the one I'm referring to is this one. Yeah. Part 10. Yeah. So B is idempotent. Yeah. And then you have that it's following chi-square of P. P is the trace of the matrix that for B. Yeah. Any other question or yeah?
So this one just follows the chi-square B.
Yes, chi-square of trace of B. Yeah. In this case, trace of B equal to 2. Yeah. Yeah.
Do we also need to show the other condition? I think there's another one with the
What is the other
that
condition?
you just showed. I think it was like mu transpose B.
If B and then yes, in our case, the mean vector is actually just a 0. So so mu B multiplied by mu is equal to 0. So yeah. So what I meant is that this mu here. Okay, then I see. So this is our mu, right? So you want to use that? Yeah. Yeah, you will need to calculate that. Yeah. So maybe just let's verify that. Okay. So 1, -1, 0, and then 1, 1, 0, 1, 1, 0, 0, 0, 2. Yeah, so it should be equal to 0, right? Yeah. If you expand this, don't forget there's a 1/2 and then also the 1, yeah. Yeah, I thought the mu is already a 0 vector. Yeah, but in our case, this is not a 0 vector, so you need to show that it's going to be 0. Yeah. Yeah, but the key is that you need to find out what do you define as B, and then the matrix B, and then verify these, and then you can just apply the theorem here. Yeah. Good. Any other question or comments? Okay, then for question 5. So again, bivariate normal, mean of mu1 and mu2, and then covariance matrix, and then we have a Q, and then we have a chi-square. Okay, so here, similar idea. We saw expression for Q, and then we're going to rewrite that as the matrix vector multiplication. And then we're going to show that it follows a chi-square. So similar strategy, but just a slight some variation on the non-central parameter. Yeah. So yeah, here let's write down the question for sigma. Yeah, so the sigma matrix is sigma 1 and then row sigma 1, sigma 2. Same for here. That's that. And let's calculate the inverse for that. So we can just use the formula for the product of the diagonals. Yeah, everything here just the formulas. Here calculating the inverse of the matrix. Okay, so the reasons that we need to calculate this is that our goal to rewrite our matrix, our expression for Q, for this one. So instead of starting from here, maybe let's examine this particular expression. So X transpose sigma inverse and then X. Yeah, so we have x1, x2, and then multiply by this sigma inverse matrix. minus a row and then one copy in the denominator. Same thing here. And we only, yeah. So here I'm just copy paste here. Square, and then x1, x2. Yeah, so here we have 1 by 2, 2 by 2, and then 2 by 1. So here, if you express this form here, you will get the formulation of Q that is given in the homework. So you should have three terms altogether in the end. Yeah. Is there any question up to this point? Yeah. So what we did here, just we re-express Q here again in a vector matrix multiplication, similar as what we did in the first part, X transpose B multiplied by X, except that this case, the B here is sigma inverse. Yeah. Yeah. So if we use X multiplied by sigma inverse, which we evaluated or we formulated in here, and then multiply by another copy of X, we'll get this formulation. And then it turns out that that's the formulation of the Q from the question. And then X is going to follow a multivariate normal, in our case, bivariate normal. So we know that the X transpose sigma inverse X is going to follow in chi-square degree of freedom 2. And with the non-central parameter, okay, maybe let me back up a little bit. So this is the random variable X that follow a bivariate normal. Now let's define a matrix V, which is the 1/2 of the sigma inverse multiplied by X, so that V is also going to follow a normal with a sigma negative 1/2 multiplied by mu, but here we standardize the covariance into our identity. Okay. And then we have the V transpose V following a chi-square degree of freedom 2. But the chi-square, the non-central parameter should be mu transpose mu, except that the mu in our, maybe I'll use mu star multiplied by mu star. So this is our new mu here after we take this transformation. So we should have a mu multiplied by sigma of 1/2 multiplied by negative sigma of 1/2 and then multiplied by mu. And that is just the mu transpose sigma inverse mu for our the non-central parameter. And this is I'm not. Does that make sense? It's just the same as the scalar case when you have a mu and then 1 for X following normal, and the chi-square is just essentially the mu square with the chi-square degree of freedom. Maybe n in this case. Yeah. Yeah. So the non-central parameter is always the new mean value taking the square. That's for the univariate case. But for our multivariate case, it's just the mu transpose mu, and then the mu should be referring to the new the mu after transformation. So you need the 2 copies of that, and it ends up with this one. I'm not sure if that makes sense or is new or to you guys, or okay. Yeah. Yeah, so in back to the question, the Q is just following a chi-square of that, and then mu transpose sigma inverse mu. There's another part referring to when does this follow a central chi-square. That would just be when the mu is equal to a zero vector. So yeah, if you think about it, if you started with a central normal distribution, then you take in a transformation and they get the chi-square. Of course, it's going to be a central chi-square. So yeah, so yeah, again, the mu when it's equal to 0, you will end up with a central chi-square. Yeah, but that is making intuitive sense. If you started with a central normal, then in the end you should get a central chi-square. Yeah. So maybe just write down the one that so if y is going to be a normal with a particular mean vector of mu, when this mu is not equal to 0, and then with an identity, then mu transpose y transpose y is going to follow a chi-square. Let's say this is n here. Then you will have a degree of freedom n, but the non-central parameter is mu transpose mu. So this is the formulation that we use in here. Yeah. Of course, if you originally, when you started from a central normal distribution, then in the end you will have a central chi-square. Okay, so I think that should conclude homework 8. Any question? Yeah, so what we did in the rest of the homework 8 is that we have an expression, and then we're going to express as a quadratic form, like a matrix vector multiplication. And then we either use the theorems or using these normal distributions of quadratic forms to get our distribution here. So that would be the overall idea, high-level idea. Yeah, any question? Yeah. So let's take a look at homework 9. Yeah, so for exercise 1, it's basically the same as in the lectures. Do you guys want to still talk about it, or maybe we can proceed to exercise 2? Up to you guys. 2, okay. Anyone else? Sorry, start with exercise 2, or?
Yeah.
Sure. Anyone else? If anyone want to, or if there's any like comments or questions regarding exercise 1, then maybe we can talk about it. Some of the details. Any thoughts? Okay, if there's no much, then maybe I'll just start with exercise 2. Is that okay for everyone? Good. Yeah. So exercise 1 is basically just from a lecture, so you can just referring that if you have any question. So yeah, consider multiple regression model. X beta plus sigma, and sigma is also a n-dimensional normal. So we have the y for the n-dimensional normal. So our parameter of interest is that the unknown beta, the coefficients for the linear model, and also the sigma square that is coming from the residual or the error term. And we have the unbiased estimator of that, and then is A transpose beta hat and efficient A transpose beta true. Okay. So in this exercise, we're going to use the what is we called here the information inequality for multi-parameter case. So we're going to use this kind of concepts to find the variance, and then let's see if that will reach the lower bound, and then we can claim that that can answer whether this is an efficient estimate. So that will be the high-level strategy for this one. Okay. So to calculate that, we first need to calculate the variance for theta, where theta here is defined as the beta hat and then the sigma square. Hat. Okay, so again, to calculate the information matrix, start with the log likelihood function, or the joint likelihood. So yeah, here's the function of the parameter. And this is going to be a normal distribution, negative n over 2. And identity, and exponential. So we have the determinant of identity, but just turns out it to be 1, so I'm not going to write it down here. Yeah. And then we have the negative 1 over 2 sigma square y minus x beta transpose y minus x beta, closing that. Okay. So this is just a formulation of multivariate normal. Let's take the log of that, and then we have n over 2 log of 2 pi sigma square minus 1 over that. Yep. And let's see, maybe we can just further elaborate on the quadratic form here to multiply for each of the terms. So n over 2 log of 2 pi sigma square 1 over that y transpose y minus 2 copy of y transpose x beta plus beta transpose x transpose x multiplied by beta. Okay. So here I'm just writing down the multivariate normal and then taking a log transformation and then calculate this quadratic terms for each of the terms here. Yeah. Okay, then to evaluate the Fisher information matrix, we are going to calculate the negative expected for the second order derivatives. So we have 2 parameters, so this matrix should be a 2 by 2, number of parameter by number of parameters. Okay, so for the 1-1 entry, let's take the derivative for with respect to mu. So we should have let me consolidate some notation here. Okay, not mu here, it should be beta. So we have an explicit formulation for the parameter. One is the beta hat, and then one is the sigma square. Yeah. So if just to make the connection, so y is following a normal with this mean vector equal to x beta, but x here is a data point. It's a data, so they are considered as fixed. So that's why the only unknown or the parameter that we evaluate is the beta hat in this mu vector. And then we have the sigma square and the identity, and this is the one that we are estimating. Yeah. So just to make it more precise. Yeah, you can also take the derivative with respect to mu, but you need a second chain rule for d mu, d beta. Yeah, but here we can just take the d beta. Yeah. Does that make sense? We're still, the log likelihood again is the function of the parameter, and then we are taking a derivative with respect to the parameter of interest, and then to calculate the Fisher information matrix. Yeah. Okay, so d beta. So the first thing that's not involving beta, we have a 0 minus 1 over 2 sigma square, and then minus 2y transpose x, and then plus 2 of x transpose x beta. Okay. And then we also need the second order derivative. d beta, and then another d beta hat. Maybe not. Okay. Just to make it more rigorous, maybe I not put the hat notation here. So without the hat notation, that means we still consider this as a unknown parameter. Okay. Okay, so taking a second order derivative, we should have a 1 over 2 sigma square. This becomes a 0, and then you have 2x transpose x. So x transpose x. Okay. So that should be our 1-1 entry in our Fisher in this Fisher information matrix. And now let's take a look at the 1-2 and the 2-1 entry, which is the first order derivative with respect to one of the parameter, and then the second order derivative with respect to the other parameter. So what we want is that d beta first and then d sigma square. Okay, again, it's up to you if you want to take the derivative with respect to sigma or sigma square. But just make sure you have a consistent operation along the way. Yeah. So coming back from here, for this first order derivative, we take the derivative of the second order with respect to sigma square. So we have -1/2 -1 sigma square raised to the power of -2, and then the rest is just the coefficient multiplied by that. X transpose x beta. Okay, let's see. This 1/2 can be cancelled out. This negative sign cancel out. So we have sigma 1 over sigma raised to the power of 4. And then the 1/2 cancel out. So y transpose x, there's a minus sign here. Y transpose x plus x transpose x beta. I think that should be the second order derivative. Anyone notice any typo, or because I'm yeah, but I think that should be it, right? Yeah. Okay, so we have the 1-1 entry taken care of, the 1-2 and the 2-1 entry. So we're only missing a 2-2 entry. So for that, we need to take the derivative of that with respect to sigma square. Okay, so that should give us -n over 2, and then 2 pi sigma square multiplied by 2 pi, right? 1 over that multiplied by 2 pi. And then there should be let me here. So just in case I made any typos, so I'm going to do it step by step. So we have the -1 from power, and then sigma square raised to the power of -2, and then y minus x beta transpose y minus x beta. Yeah, so let's further simplify that. We should have a -2 sigma square, n over 2 sigma square, and then plus a 1 over sigma raised to the power 4, and then for y minus x beta transpose that. Yeah. Sorry? Oh, yeah, sure. Like, is that okay? Yeah. Yeah. So here we're working again, just to intermediate summary, we're working on the 2-2 entry for our Fisher information matrix. And then we're just taking the first order derivative with respect to sigma square. And then we end up with that. Yeah, it might feel like a little bit tedious, but bear with me because these are just some algebras. Yeah. Yeah, and then we need a second order derivative. So we have a negative sign and then -1, n over 2 sigma square raised to the power of -2. How should we work on this one? Yeah, so here, just in case if there's any, so this one here is actually the sigma square raised to the power of -2, and we are taking derivative with respect to sigma square as altogether, so we will need a -2 here, but sigma square raised to the power of -3. So it might make a difference if you are taking derivative with respect to sigma. So that could cause some, will give you some differences here. But yeah. Okay, so negative sign for that, raise the power of that. Okay, and then simplify, we should have n over 2 multiplied by sigma raised to the power 4, and then minus a I feel like there's a typo here. Did someone notice anything? I'm missing a I'm missing a 1/2 here. No wonder. Yeah, so the 1/2 is referring to this one. When you started with the log likelihood function, there's a 2 multiplied by sigma square. Yeah. So yeah, so that 2-2 entry should start from the log likelihood function from here. So you need to take derivative of that. Yeah. What I did wrong is that when I scroll up, I miss this 2 in the denominator. So there's a 2, 1/2 here. Yeah. And now, yes, there should be a 2, there should be a 2. And then there should also be a 1 over 2. And that should cancel out. So you should have sigma raised to the power of 6, 1 over that, and then 1 think now should be good. Okay, so now we need to evaluate the Fisher information matrix, which is defined as the negative expected value for all of the 4 terms that we calculate. So now we're going to fetch each of the terms that we get. So the 1, 1 entry, let's see, should be this one. Negative 1 over sigma square x transpose x. Okay, and the 2, 1 and the 1, 2 entry should be this one. So 1 over sigma 4 negative y transpose x plus x transpose x beta. And then you also have the same thing here. Let me know if you think there's any typo, because I'm always doing from scratch, so yeah. But so far, is there any typo or issue regarding the calculation? And n over 2 that minus 1 over sigma raised to the power of 6 y minus x beta. Okay, I think that should be an intermediate result. Next, evaluate the expectation. So let me ask a question. What is the random variable that this expectation should be considered? So what should be considered as random variable here when we evaluate this expectation for the Fisher information matrix?
Y.
Yeah. Do you all agree? So yes, y is the random variable, and I follow a normal with what is the mean here that we already show on the top.
X beta.
X beta. What about the variance?
Sigma square I.
Dimension of
N.
n. Yeah. Do you all agree with that? Yeah. Okay. So yeah. So whenever you see or whenever you calculate the Fisher information matrix, when you evaluate this expectation, although with long tedious steps, just taking derivative again and again, and then just double check, don't make any typos, or when you scroll up and down, and then maybe you will miss a constant. But besides that, and then when you approaching this step, ask yourself what would be the random variable here. Once you think about it, and then you know how to handle this expectation. So you will have one random variable here, one random variable here, one random variable here. And that is the 3 terms that you need to consider or to worry about when you evaluate the expectation. Okay, so first, yeah, go ahead. Yeah. Sorry, what?
Why would Y be?
Because our model, maybe I'll write it here. So we are given a data X, and then we want to, using a linear model, to as a model to learn about this data. So what we have is the y equal to x multiplied by beta plus epsilon. So x is actually considered as our data, so it's fixed. And then beta is the parameter that we want to learn. And the epsilon here is the normal with mean sigma identity. So that give us that kind of like give us that y is also a random variable that follow a multivariate normal.
So why aren't we like treating beta as random variable, since we are also learning beta?
Sorry, I can't hear you.
Why aren't we treating beta as random variable?
We're not treating beta as random variable. Beta is the parameter of this model that we want to learn, that we want to estimate. So beta is the parameter of this linear model. So although it's maybe you heard people saying there are lots of machine learning models, or this can also be a very simple. This is also a very simple model, and then the model is parameterized by beta. So beta is the parameter that we want to learn, and usually the beta is, or the parameter of say a neural network or something, is all coming from data. So all the x and the y are coming from the data. Yeah. So you usually have like a tabular data, like feature 1, feature 2, or something, and you also have a predictor, like for y. Yeah. But when we work on the model in general, this y here is essentially a random variable that follows distribution. This y is only part of the data that you collected, that you observe when you collect the data. But so you can think of it as there are lots of data that you still haven't collected, and then they serve as the randomness there. Yeah. So y is the random, or is a distribution there. I'm not sure if that answers your question. Another way to look at that is that we define the model in this way, and then we have some error term that is not explained by the data, and we assign that's a distribution that we impose by the modeler, by the researcher, and then we just shift this normal random distribution by x beta, and then it gives us that y also following a normal distribution. If that would help you to, that's another way you can look into this as a random variable. Yeah. Yeah, so once we recognize that we're regarding y as the random variable, then you just make sure when you evaluate that to to work on, when you evaluate this expectation, just bring the expectation to the corresponding position. So for example, this y here is just x transpose. So in the end, you will have x beta transpose, and then multiply by x. So you have a beta transpose x, and that is the same as this one. So this thing, when you evaluate the expectation, it will goes to, maybe I'll write it here. So the Fisher information matrix, when you evaluate the expectation, these two becomes a 0. The reason is that when you plug in this expectation to here, the y, you need to evaluate the expected value for y, and then the expected value for y is x beta. So when you plug in here, you have beta transpose x, and that is just this thing here. So you have, that will make it to 0. Same thing for here. So the 1, 2 entry and the 2, 1 entry, after you evaluate the expectation, they will become a 0. This thing does not involving randomness, so you have the same constant, x transpose x. So the tricky part is regarding this one. You have a quadratic terms. So one way you can work on this is consider this as a q. So you will have the expected of q transpose q. And then there are a few ways you can do from here. One is that you notice that this is 1 by n, n by 1, so it's a scalar. So you can do expected of trace of q by q, q transpose q. And then that will give you, do I still need to talk about the details? I think that's just the same trick that you used before. And then, so that should give you, maybe I'll just provide the answer here. Does that make sense? Or so after you evaluate this expectation here for this quadratic term, you will have n over, 2 multiplied by sigma raised to the power of 4 minus a 1 over sigma raised to the power of 6, and then the expectation of this. And then if you want to use this, you can also solve that. That will give you n multiplied by sigma squared. That is the expectation of the trace of the q transpose q, if you want to use this way to solve it. But there are also other ways that you can evaluate that, and then you can simplify from there to get the 2, 2 entry. Yeah. Yeah. I'll stop here, and then yeah, let me know if you have any question or comments. But yeah, the procedure are should be very similar to what we did in previous homework.
Is this the last time we'll see you?
Maybe not. You still see me for the final exam.
See you then. Thank you.
Yeah. Yeah. Again, don't worry.